Hello, and welcome back in our foundation engineering class. So we're going to continue, I think, with the same chapter. Just information. This is my email address. You can reach me anytime. And the link for the two YouTube channels, the English one and French one. And this is my WhatsApp. Okay. So if you want to reach me, any of these will be okay. So today we are going to continue with the same chapter number 1, which is about soil mechanics applied in foundation engineering. And in today's video, we are going to talk about the same about compressibility and settlement of soil, okay, which is part of the strength of the soil, which is part of strength of soil, compressibility and settlement of soil. That also is very important, a very important matter in terms of foundation engineering, okay. So what do we know? We know that once we apply load on soil, okay, the soil undergoes deformation, and that will cause settlement of your structure, okay. Then if you are dealing with dry soil, then the settlement will happen very fast, it quick, okay. After loading, the settlement happen faster than when the soil is not dry, okay. So in that case, we can describe the behavior, the settlement, as elasticity theory, with using the elasticity theory, okay, even if the behavior is actually more complex than elasticity theory. So when the soil is wet, fine grained, fine means, for example, clay, okay, wet fine grained soil. In that case, the settlement will take longer time, and the reason is because of slow water drainage and also the adjustment of soil particles, okay. So this is considered as primary consolidation, okay, and we will talk especially about this one in this video. So for certain soil, some other soils, the settlement will continue even after the pore water pressure reaches, because we said here water will drain, right? After applying the load, the water will drain. It means immediately after applying the load, the pore water pressure will play a significant role in the supporting the load, okay. And after the pore water pressure reaches equilibrium, for some soil, the settlement still continue with the surroundings, okay. In that case, we will talk about secondary compression or secondary settlement, okay. The primary compression is mainly due to the first stage of settlement, which is sometimes for clay is associated with water drainage, okay. So if there is water in your soil, fine grained soil, once you apply load on that soil, the water will carry part of that load. And if the water starts being drained, the water will give the load slowly to the grain of soil. Okay, so it means if the water is totally drained, the total amount of the load will be supported by the soil itself. Okay, that's the meaning. So during the drainage of the water, you will see that the load will be transferred to the soil and the soil will be settling, okay, until the end of the drainage. That part is what we are calling here primary consolidation, okay? So, but some soils, even after the water drainage, they still continue to settle. The settlement will still continue because due to some like arrangement of the soil particles, and even sometimes the soil particles themselves will crush and reduce volume. So that is the secondary compression, secondary consolidation. So for this secondary consolidation, we will discuss this later. But the first consolidation, the primary settlement, will be discussed in this video, okay? The primary and secondary settlements, consolidation, compression, if you want, can sometimes overlap, and it will be difficult sometimes to separate them, you know? Okay, so as I said, in this video, we are going to talk about immediate settlement, which is primary consolidation, okay? Immediately after loading, and the settlements will start. That one can be estimated through field tests or through lab tests, okay? And there are some formula to estimate that settlement, okay? So this is what we are going to discuss here now. Right? So immediate settlement in soil, as I said, it's typically we use elastic theory to deal with it, even though the actual behavior of the soil is not really elastic. Okay, so to simplify things, we use elastic theory. Okay, the only problem with that is there are some property of the soil, very precious value. Some precious value of some soil property are difficult to obtain, like elastic modulus, portion ratio of soil. To obtain this, sometimes it's a very big challenge, okay, due to sampling and stress related factor. But some people use field tests to obtain the settlement. This, for example, plate load tests for if your foundation is footing on granular soil or unsaturated clay. So within these two, please notice that there is no saturated clay in this for plate loading test. Granular soil, for example, sand or gravel, it's okay. Unsaturated clay, maybe okay. If you are dealing with saturated clay, it's not included in this first part, okay? The second part of this video will be about saturated clay. So the first part will be for granular soil. The formula we are showing now. So this plate load test, what does it look like exactly? We have, actually there are several devices. This is just one example, okay? Yeah. So it look like this, and we apply pressure, the plate, and we measure displacement in the time, okay? The settlement can be measured in the time by applying. So some people use just something like this, a machine, to perform the test. there are several ways to do it, please. Okay, you can check by yourself. Some people use this like loading. These bags are like sand, field of sand, and the device is inside. The illustration is here. This schema give you a perfect illustration. In the hole, this you see this hole is the plates will be there according to the depth where we want to know. Maybe this is the feature level of the foundation of the footing, for example. Okay, so these bags are represented by this. Okay, sandbag, and these are the loading. So this way you can get maybe actual settlement that your foundation will undergo after building the foundation. Okay, somehow. All right. So the equations for this, because it based on elastic behavior, even though the behavior is not really elastic. Here is equation. SE is settlement. Okay. This equation, this alpha is the factor determined in this figure. So L, the ratio L bar B, L will be the length of your footing, and B is the how large the footing is, the width of the footing. And here is the factor alpha. Okay. So depending on the ratio L bar B, you can determine the alpha, the value of alpha. Okay. And B, as I say, the width of the footing. L is the length of the foundation. Okay. So L divided by B. So don't ask me, please, if it is a square footing, what will it be? It's very simple. It will be just 1. This ratio will be 1. Okay. It will be here in that case. Yeah. So Q0 is the contact pressure, means the load, maybe this is surcharge. B by L is just the area of your footing. Okay. The surface. B multiplied by L. B by L is just the surface of the footing. Okay. And P is maybe the surcharge. So Q0. This surcharge P may be due to the soil. And this, of course, is settlement, immediate settlement. And ES, this one, ES, that is the parameter that is sometimes difficult to obtain for a soil. So ES is elastic modulus of soil, and VS is Poisson ratio of the soil. Okay. This one, F, is 0.5 or 1, depending if we are considering settlement at the corner of the footing or center of footing. Okay. If it is center or it is the corner, because sometimes the settlement is not same. It's very simple because where you are applying load is center, right? Where you are applying load is center. Normally for centric loading. Of course, there are some cases where the load is applied with a bit eccentricity. Okay? But we are supposing here that this load is applied in the center of the footing. Okay? So in that case, this is what. All right, this is the formula. The first formula you can use to estimate the settlement. Okay? Immediate settlement, please. Precise. So as usual, I will put this formula here for us. So if you used to watch my videos, you know that once we finish with formula, we put it here. Okay, this is the formula we just established. So Another method, another widely used method for granular soil. Once again, I repeat, this formula is for granular soil, okay? Sand, clay, or maybe unsaturated clay. So this method is used also. This formula also is used, okay? So this one, IZ, is a strain influence factors which can be obtained with this. It is applied for square or circular footing, and we can find it here in this figure is showing the value you can obtain. Okay, so this is the value you can read here. As you can see here, it's written 0.6. Okay, so maximum here is 0.6. So imagine that here is 0. Okay, so it means depending on the depth, okay, the peak being at depth of 0.5 times the B. This is large of the footing. Okay, so you can read the value depending on the depth. You read, for example, if you are here, B, because this is 0.5 B, this will be B, 2B. Okay, if you are here, you can read this value, corresponding value here, and you will know the value of IZ. Okay, the C1, this one, is given by this formula. 1 minus 0.5 Q delta sigma minus Q. So this Q is, I think, the sharp charge, and delta sigma is the stress caused by the the sharp charge. Okay, that one is very simple. Just sigma gamma by Z. Okay, where the stress in soil, gamma total stress, so gamma multiplied by Z, you get this one. Okay, yeah, and Q is the same Q here. So C2 is this one obtained by this formula, 1 plus 0.2 log the time here in years divided by 0.2. Okay, so if you want settlement, for example, for 10 years, okay, you can put here 10 divided by 0.1. If you want settlement, you are calculating settlement for 20 years, then you put this here, 20 here. That is the meaning. Okay, so 1 plus 0.2 logarithm. So sigma, this one, is the total weight divided by the surface, B by L. Okay, B multiplied by L. P is the load. I hope what I said here it was understandable. P is the load. Q is this one, gamma multiplied by Z. Okay, and this is elastic modulus, Poisson ratio. F, same as the previous formula, 0.5 or 1, depending on where you are applying, where you want corner or center. Okay, sorry, just to go back. So the Q here is the sharp charge, okay, overburden stress. So gamma multiplied by Z. So depending on where you are at which depth you are paying the corresponding Q. And also this P sigma delta is the variation of stress. which is the load you are applying divided by the footing surface. So P divided by B multiplied by the L, which is here. Okay, the Q here is this one. The sigma delta sigma here is this one. The same Q here. Okay, so please don't be confused. Okay, so we had this formula before, and now we have another one here. So I put the two formulas here. So as we said, the main issue people are making this difficult, the application of this formula difficult, okay, is the elastic modulus, this one, okay? That one is sometimes difficult to obtain for soil. So we found this table that giving this value, not only elastic modulus actually, the V also, the percent ratio also is sometimes difficult to obtain. So these are some typical value for different type of soil for the two parameter here, elastic modulus and the young modulus. Okay, for the young modulus, the not young modulus, so modulus is this one, elastic modulus. The percent ratio. Okay, the percent ratio is given here. Clay, saturated clay, unsaturated clay, sandy clay, silt, sand, gravel. Okay, I'm sure that you can read all this. So just read and see they give just ranges. Okay, not exact value, not because it's changing depending on the several situations. And for the elastic modulus, the young modulus, it's here some ranges for different type of soil: soft clay, medium clay, stiff clay, loose sand, medium dense sand. Okay, so this is just example. If you don't have possibility to estimate exact value of these parameters, maybe you can use this table. Okay, I hope you remember this figure, right? Remember this, where you can estimate the IZ of this formula. So the thing is, sometimes we need to bring some modification to this figure. As you can see here, it's starting maybe from 0 here, and the peak is obtained at 0.6, and then it decreases like this. Okay, sometimes you need to change it and start from, instead of 0, start from 0 and 0.1, means around here, not exactly 0, 0. Okay, and the peak is sometime, instead of 0.6, we choose sometimes 0.5. Okay, just modification 0.5, but still 0.5 times B here, like it will be around here. You see, this is 0.6, so 0.5, I'm not sure exactly, but it will be here, and so on. Okay, so when you are dealing with strip footing, sometimes the coordinate of the peak this one, and the bottom, this bottom one, it changes. The coordinate change. For example, the peak, instead of 0.6, sometimes it goes to 0.7. Okay, And instead of 0.5 B here, it comes here, B. So it will be around here, B and 0.7. So you will have something like this before it goes here. And the bottom, this point, instead of 2B, it will be 4, means twice this distance, deep down here. Just some modification sometimes. But when we will start to apply this, maybe it will be easier for you to understand. Yeah, anyway, now we are talking about elastic property and in situ test parameter. Because as I said, the main difficulty is to obtain this Young modulus, the elastic modulus of soil. So sometimes people use in situ test to obtain this from the in situ test. So the most common use in situ test are CPT and SPT. Okay, so these two will be discussed in chapter 2 in detail. Okay, there are some relationship for this in this table. Okay, for these are for SPT and this is for CPT. Okay, for sand, normally consolidated sand, you can use this formula. If you have the n value, the SPT n value, I hope you know what is SPT n value. But if you don't, the next chapter will be mainly for this kind of thing. Okay, field testing. So CPT, the QC from CPT test also. So for sand, SPT n value, QC, you can obtain this. Saturated sand. And normally consolidated sand, over consolidated sand, gravelly sand, clay sand, silt sandy, and silt or clay silt. Okay, anyway, these are the formula you can use. And these value, for example, C, I think this one is used in Japanese standard. This one. But please check. And also, sometimes these following formula are used. And con resistance and CPT n value, they force this formula in kilopascal, 768 n value. So if you have your CPT n value, multiply it by 768, and you will obtain average elastic modulus of your soil. And if you do SPT, if you do CPT, sorry, this one is SPT, okay? N value is for SPT. I hope I didn't otherwise. I didn't say otherwise. And this one, QC, is for CPT, cone resistance. So if you have your CPT, cone resistance value, multiply by 2, and you obtain the elastic modulus. Okay. So this, once again, for granular soil or maybe unsaturated clay. Okay, please don't forget, mainly for this. So now let's go for saturated clay. When you are doing with clay that is saturated with water, then everything becomes different because this saturated clay is very difficult to deal with. Okay, so once you have that, you have to be careful and it changes. In that case, this figure is explaining, for example, that when the clay is saturated, for example, here is water level and the ground level is here. You have here sun, for example, this is sun and this is clay. This clay layer is a problem. And bedrock here. So in that case, once you load, you see load here. After loading, the water in the soil will immediately take some part of the load because the water will not be drained easily because of this clay layer. It doesn't matter where the clay layer is. Once you have clay, saturated clay, it's saturated because the water level is here and clay is here. So if you have that, when you load, the load is immediately taken by the pour water, the pour water pressure, the pour water, okay? So, and then during the dissipation of the pour water pressure due to drainage, because the water will drain, but very slowly. The water will drain. While the water is draining, the load will be transferred from the soil, from the water to the soil particles, okay? So gradually, then the total stress, the applied load will be transferred to the soil skeleton, okay? Soil particles as effective stress, something like this. So effective stress is the actual stress that soil particles are receiving. I think we have explained all this before, okay? We have explained all this before. And the pour water pressure will take some part of the load, and during the dissipation of the water, it will transfer that load to the soil little by little, to the soil skeleton, little by little, okay? As you can see here, for example, this is the initial pour water pressure, for example, okay? So it means this is the total load that the water will take initially. And at the end, the final pour water pressure will be like this small one, okay? And it is here. So it means all this part, when the water will drain, this part of the stress will be transferred to the soil skeleton. Yeah. Here is when we have equilibrium of the pour water pressure. When we reach equilibrium of pour water pressure, the profile of the pour water pressure will be like this. And initially it was like this. It means this part will be transferred to the soil skeleton, which will be here. As you can see, it's same here. Okay, so it means that this will be the increment, load increment, okay, which was supported at the initially. You have this effective stress. Effective stress is the stress supported by the soil particles, soil skeleton, okay, initially here. At the same time, initially, this water pressure is supported. This is the part of stress supported by the water, okay? But when the water will drain. This amount water will drain means the amount of water will decrease. This amount of stress will be transferred to the soil particle. It means the effective stress will have this increment and decrement here. So minus here. This is final. Final effective stress, final pore pressure. Means equilibrium. Okay, this is how it works. So sometimes this transfer will take long time. So long-term rearrangement of soil skeleton, for soil skeleton after the water is gone, power pressure, equilibrium of water pressure, then the arrangement of the soil particle will start, and the consequent foundation settlement that take place during this process is, we call this a consolidation settlement. Okay, so the water is going, soil particle will undergo some rearrangement, and this will cause a settlement of the clay, of the saturated clay. So this settlement is what we are calling consolidation settlement. Okay. Consolidation settlement. So this consolidation settlement can be measured in the lab. Okay. The magnitude and rate of consolidation settlement can be obtained. We call this laboratory one-dimensional 1D consolidation test. This is apparatus to do the test. So you put the soil sample here, the weight, this one, you can see some weights here. This is a photo from Wikipedia. If you put the weight, constant load, constant weight, then you record. The soil sample has this dimension, okay? The diameter is 62.5 millimeter, and the height of the sample is 25 millimeter, okay? It's just what you are seeing here, this, okay? And you fill it with, there are, maybe we'll come back on this. There is whole, another program for lab and field testing. And we record, during this, we record the deformation and also sometimes pore pressure, okay? And result means the deformation that will result from the test is called ultimate primary settlement. And during this, we will drain water from everywhere, okay? From all direction, the water is drained. So the sample is then tested for wide range of stress, and you choose a stress according to expected average pressure. Increase the footing your foundation will experience during its life on the construction site. What is average pressure increase produced by the foundation in the clay layer? The previous slides I show you granular soil layer and clay layer. What is the amount? Let me go back a little bit. I think this figure, what is the amount of stress that this clay layer will receive? Okay, average. According to that, you will also do your test, your 1D consolidation test, according to this type of stress, this amount of stress. Okay, so as you can see, there are different weight load here. You can change, and here is the loading farm. Okay, so this figure 17 is the result, what you are obtaining. Deformation in millimeters and the time. Okay, so the beginning, you have maybe it decreases once you are loading. Uh, how to say? You load and you record the time and the deformation, the millimeter in millimeter, how it will decrease, the sample will deform. So the coefficient of consolidation, CV, for soil can be obtained from this by using this formula, this equation. So CV, coefficient of consolidation. H, this one is the longest drainage path in the consolidation, in the consolidating soil layer. So if you take this, if you remember the sample, the dimension of your soil sample, I think 0.60 something for the diameter, and the height is, I think, 0.25. Let's say 25 millimeters. Okay, let me go back and show you what I'm talking about. 62.5 millimeter and 25 millimeter. So 2.5 centimeter and 6.25 centimeter. 2.5 centimeter and 6.25 centimeter if you want in centimeter. So this H is the highest value within these two. Okay. Yeah, the longest drainage path. And T is just a non-dimensional time factors corresponding to time T, the time here. So you can obtain this C. This coefficient of consolidation is just about, let's say, consolidation rate. Okay, consolidation rate. And as you can see here, average consolidation amount, or what, let's say, the degree of consolidation, maybe. Here, U100 means it's consolidated 100%. As you can see, this figure, it decreasing like this, the volume is decreasing, displacement, you can deformation, the sample is deforming, and at certain point, it's not deforming anymore. Here, you can see, that means that you have reached 100% of your consolidation. Okay, so U100 here means 0.72 millimeters. It's here, 0.72 millimeter. Okay, and 0 initially it's here, so 1.52 millimeter. Okay, so you can know the degree of consolidation at any time. So this also can be obtained from the test, this average. And as I said, this HDR in this formula, the formula, where did I put this formula? This formula, the H is 12.5. millimeter, because the water is allowed to drain um, from all sides. Okay, the longest path of drainage of water. So we can obtain this U is average degree of consolidation. Don't forget that if you know the total amount of consolidation, it will be 100%. Okay, so this average degree of consolidation, we know we can obtain this from this experiment also, 1D consolidation test, the lab test, obtained by this. Okay, this T is the same one here. And this table is showing the amount of the percentage. Let's say it like this. Instead of average degree percentage. For example, here it means 50%, because this consolidation, this settlement consolidation, it take time. So it is like this. Of course, at time, infinite time, it will be 100%. Maybe it's all like this. This is all what we have today. And I think next time we'll try to make one tutorial based on this, the result of this test. Okay. Next time, in the next video, we'll make one tutorial, one example to estimate settlement based on this result. Okay. Okay, thank you very much. See you next time.